Kia ora, chemistry kiddos. This is Mrs. Fisher with our first video in our Redox unit for our online note-taking. My page should look like your page, and I'll fill them in and you just need to copy them down while listening. All right, we will start with the definition of redox. So in this one, our definition is going to be the transfer of electrons from one species to another. So redox looks at reactions that move electrons from one chemical species to another chemical species. Some reminders from year 11, as well as the half unit we kind of finished. Let's start with the left side of our reaction is full of reactants, and the right side of a reaction is full of products. It seems really simple, but when we use those words in our descriptions, we're going to need to be accurate. We also talked about net ionic equations, and our net ionic equations were determined based on solubility. Because we're going to have some ions in solution, and you'll need to know which ones are spectators and which ones are participatory members. Also, we need to remember when we write our reactions, you're going to have to predict the products of the reaction. So if I give you two reactants, you'll need to be able to replace the cation or replace the anion depending on which one I'm reacting it with. We also will be using ions as well as elements. So ions will have a formal charge, whereas elements have no charge. And last but not least, this is not really a thing to remember, but it's a reminder going forward, is that all non-exchange reactions or double displacement reactions are considered redox. So double displacement reactions aren't redox, and in class I'll show an example of that. Just some notes going forward, because writing out the word reaction gets quite tedious. We like to abbreviate it, so reaction is typically abbreviated RXN. So you'll see me write it that way as well. All right, let's talk about the diatomic elements. These are pure elements that form molecules of two identical atoms. We still consider them pure elements or regular elements. They just always come with a pair instead of being by themselves. So where iron you would write Fe, with diatomics you would write H2. Now there are 7 of these, so we have H2, N2, O2, F2, Cl2, Br2, and I2. So the fact that these come in pairs is evidenced by the prefix di, where polyatomics are many atoms put together. These are diatomics, which is 2 atoms put together. We also have a little mnemonic to help memorize them. That mnemonic is hecno and column 17. So, are they alone? Heck no. and column 17. I don't know, it's a silly way to remember it, but yes. All right, now let's look at your vocabulary section. So I'll just turn this guy this way. There's only a few vocabulary words that you need to be aware of for this unit. So the first one we're going to look at, spectator ions. These are ions in solution that do not participate in the chemical reaction. When it comes to redox reactions, that means that there's no change in oxidation number. Which leads us to our next one, the oxidation numbers. Sometimes referred to as the oxidation state. This is the number of electrons an atom or ion has either gained or lost compared to the neutral atom, also known as the charge. So, the oxidation number is basically just a fancy word for the charge. There are some exceptions, but when we get to identifying those oxidation numbers in a bit, you'll see where it might differ slightly from the charge. Our last word here is going to be half reactions. These are separate parts of the overall reaction that represent either oxidation occurring or reduction occurring. So, just 4 words. Sorry they're a little bit squished there. All right, I'm going to rotate us back so that we can move down, get ready for the next bit. Our next box, or last box for these notes, is going to be about calculating oxidation numbers. When we turn the page, we'll learn how to assign them, and then we'll do some practice after that. But we'll need to reflect back on this. So calculating oxidation numbers requires that you look at the sum of all of the oxidation numbers. And we look at the sum for 2 different categories. One is for neutral compounds, where the sum of all of the oxidation numbers is going to equal 0. And the other one is for polyatomic ions, where the sum is going to equal the charge. If after you use all of the rules and you are still missing oxidation numbers, then you have to use algebra to solve for x to find that missing number. Assigning oxidation numbers is the first step in balancing redox reactions, so understanding the rules is quite important. There's a couple of rules here, and we'll go through some of the specifics, but we'll start out with our unbonded elements. These are elements that are not bonded to any other elements. So, some examples are iron, silver, sodium. Our diatomics are not bonded to other elements. Even though they are bonded to themselves, we still consider them non-bonded elements. So hydrogen would be an example, and chlorine would be an example. These are all going to have an oxidation number of 0. Since they are unbonded and they have a 0 oxidation number, I have since discovered that Beyonce created an entire song to describe these, as they are single ladies, and we put a ring on them. So we'll just slide this over here. So our single ladies are unbonded elements, and they have an oxidation number of 0. Next up on our list here is fluorine. Fluorine has an oxidation number of -1 when it's bonded to other things in compounds such as sodium fluoride, in other compounds such as zinc fluoride or lead fluoride. We'll make that a fancy lead fluoride. We'll call it lead 4 fluoride. Oxygen is our next one up. Oxygen is always, 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 have I said it enough? Always -2. Except, we'll get to the exception. So, in things such as H2O or H3PO4, oxygen is always -2. Sometimes, so this little star here, asterisk, means that in peroxides, oxygen has a -1 charge. So in H2O2, it has a -1 charge. We can even throw in NO3- as an example of that one. Then we come to hydrogen. Hydrogen has 2 cases. Sometimes it acts like a metal, where it's bonded to nonmetals, where it's going to have a +1 charge. This is in such compounds as this one, and this lovely guy here. Then he's got times where he acts like a nonmetal because he's bonded to metals, where he has a -1 oxidation number in compounds such as magnesium hydride, tin hydride, or sodium hydride. Then last but not least, we get to our metals. These are also, this category also includes our single ions, where we just use their formal charges. So we've got sodium has a +1, aluminum has a +3, chlorine has a -1, and phosphorus has a 3- charge. When assigning oxidation numbers, we always start from the top of the list and work our way down when assigning them. All right, so I've put together a few examples. They're going to be on this next slide. So I'll refer back to these rules, but I won't be flipping back and forth because it's just too difficult with this program. So let's take a look. If we flip, all right, On this slide, I've put 9 different chemical species so that we can do a bit of examples and practice of assigning oxidation numbers. If we remember, the first one on our rules list that we want to assign oxidation numbers for are those that are non-bonded elements. So this first one here, those are 2 elements bonded together. This is a polyatomic ion with a formal charge. These are 2 elements bonded together. This next one, iron, it is non-bonded, and for all non-bonded elements, we're going to put an oxidation number of 0. We just write the number a little smaller on top. I usually choose a different color so that I can distinguish it from the other ones. As we look through, I also see chlorine down here. Even though he's bonded to himself, like other diatomics, he's still considered a non-bonded element because he's not bonded to anything else. That's terrible looking. 0 will make it look better. The next rule on our list is fluorine. So I've got my fluorine up here in the top left. Fluorine is always going to be -1. It's our most electronegative, which is why we start with it, even though we don't use it very often. Since I have 2 fluorines, I'm going to go ahead and make myself a note that 2 times -1, I'm going to have an overall -2 charge for that fluorine section of that compound. The next rule on our list is oxygen, and oxygen is always going to be -2. So this one is -2, this one is -2, this one is -2, and this one is not. This one is not -2, and we'll talk about it in a minute. Before I get too far into all of these, I'm going to go ahead and add up for the oxygen portions of these molecules. -2 4 times. That is a total of -8 overall for the oxygen. I'll just give that a little underline to help us out. This one here, this oxygen, -2 7 times is -14. This one here, oxygen, -2 3 times is -6. However, this compound down here is hydrogen peroxide. And when oxygen is in a hydrogen peroxide compound, that's where it does its weird thing where it wants to be a -1. So it has an overall charge of -2 here. Next on the list is hydrogen. That's our next rule. If we go through, I've got hydrogen in this molecule. Hydrogen is bonded to a non-metal, so hydrogen is acting like the metal. When it acts like the metal, it takes on a +1 charge. We don't have to write the ones if you want to just write positive because we know the 1 is understood. That is fine as well. When I have it 4 times, that gives me a total of +4. What you can't do is you can't just write 1. It has to have a positive or a negative sign. Down here as well, I have a hydrogen in this molecule. So this hydrogen is bonded to non-metals, which means it's taking the place of the metal, which means it's also going to have a +1 charge. And there's only 1 of it, so it's going to keep its +1 total. And then last but not least, I've got hydrogen over here in my peroxide. And I'm going to write a +1 here. When I have +1 2 times, that's a total of +2. Now, if you look, here I have a +2/2 and a -2/2. If I were to add them together, so the sum of these oxidation numbers in total, or these oxidation values, is 0. And you'll notice there's no formal charge up here in the corner because it's a neutral compound, and all neutral compounds have a 0 charge. The last rule we're going to look for here are my metal ions so that I can assign them their charges. I know magnesium is in group 2, which means it's going to have a +2 charge. So that means that +2 plus -2 is going to equal 0. And since I don't have a charge, that works out perfectly. The next metal I come across that's bonded is this iron here. And this iron, I have to look to see what it's bonded to. It's bonded to dichromate. Dichromate has a -2 charge. And if this iron and this dichromate are in a 1-to-1 ratio, then this iron also has a 2 charge, but it's positive because it's a cation. Then I have any remaining ions that I can assign their formal charge. The only ion that I've chosen to be on here is this iron, which has a formal charge of 3+. So this one has an oxidation number of 3+. So you can see here I have this iron, which has a 0 oxidation number. This iron has a 3+ oxidation number, and this iron has a 2+ oxidation number. All of them are iron, but all of them have different oxidation numbers as we follow the rules. All right, we've still got a couple of missing ones. We have this sulfur doesn't have an oxidation number. This carbon is missing, and this nitrogen and this chromium. So the way we're going to solve these is we're going to use a little bit of algebra. I want you to see if you can solve it on your own to find x with the information that I've given you, and then I'll go over it a little bit more thoroughly in class. All right, that's it for me. I'll see you in class. Fisher out.